Good evening, everyone. Welcome to the seventh interactive session on strength of materials. So this is seventh interactive session. So today we'll be looking at strength of materials, problems on buckling, and the Castigliano theorem. I'm Naresh, a research scholar in the Department of Civil Engineering at IISc. So let us get started. So the reference for whatever I'm covering today are from this book, Introduction to the Mechanics of Solids by Crandall and Dahl. It's an old book in Mechanics of Solids, and it's a very good book. So the strength of materials part, where we look at solving for forces and the stresses, that I have taken from chapters 1 and 2. And chapter 9 deals with the stability of equilibrium conflict, that is buckling. So the first part that we are going to look at today is steps to solve problems in strength of materials. For those of you who have attended my previous sessions, I would have already enlisted the steps for solving problems in engineering mechanics. In strength of materials, we have a few more steps. So as always, the first step given any problem is to state the knowns and the unknowns in the problem. You may be given a structure that is subjected to some support conditions and some forces. So the first step is to state the knowns and the unknowns. This applies universally. You can use it for the GATE exam or anywhere in general. The second step is to draw the free body diagram of the structure. Free body diagram by isolating every part. So we need to isolate the parts of the structure. And when we do that, suppose we isolate this and draw the free body diagram, we need to indicate the unknown forces and their reactions. So indicate the unknown forces. Unknown forces and moments. As the third step in engineering mechanics, I would have said that you need to enforce the equilibrium equations. So here also it's the same thing. In general, we have governing equations. For the equilibrium of rigid bodies, we need to enforce only the equilibrium equation, the global equilibrium equation, which is sigma fx equal to 0, sigma fy equal to 0, and sigma moment about some point in the z direction equal to 0 for a two-dimensional problem. But when we deal with deformable bodies, we have more governing equations than the equilibrium equation. So what are the governing equations? The first one is, of course, the equilibrium equations. The next is the relationship between the forces and displacements. So we have what is called the force displacement or the stress strain. Depends on the type of problem we solve. If we are solving a problem that involves only an assembly of springs, you can do well with the force displacement relations. And if you're solving a continuous body such as a beam or for example, in the case of a beam, you can get away with the moment curvature relation. And if you're dealing with three-dimensional continuous bodies, we need to get to the stress strain relations. So some kind of relation that relates the displacement quantities to the force quantities or the stresses to the strains. So the next thing is to enforce the force displacement relations for the stress strain, depending on what problem we solve. And the third most important thing that doesn't appear in the equilibrium of rigid bodies and in statically determinate problems is geometric compatibility. What does geometric compatibility mean? Geometric compatibility means that the unknowns, the displacement which we look for, the solution that we look for, the displacements in the solution that we look for, must satisfy the specified boundary conditions and other constraints. This will become clearer as we solve problems. So the third condition is geometric compatibility. These three governing equations will always be enough to solve for all the unknown forces, moments, displacements, whatever in the given. So there is no question of if the structure is statically determinate, indeterminate, rigid, deformable. In any case, these steps are valid. You just state the unknowns, draw the free body diagram for every single part of the structure, and then enforce the governing equations. If it is a rigid body, you have only the equilibrium equations. If it is a statically determinate body, we have the equilibrium equations along with the force displacement relation. And if it is a statically indeterminate body, we have to enforce all the three. So this is in general. If you have any doubts, you can ask. You don't have to wait. You can always interrupt, and you can ask if you have any doubts. Let me go to the next part. So the alternative way to solve for these problems in statics is using the Castigliano theorem. So what does the Castigliano theorem say? Suppose we have a body or a structure. It is supported in some manner and it is subjected to some forces. Let us call them F1, F2, F3, and so on. Now, as we increase each of these forces from 0 to a value F1, if it is a linear elastic structure, if we are doing linear elastic analysis, the forces are proportional to the displacement. So let these be the displacement delta I, and let it be the force Fi. And as we know, the integral F d delta. So if we integrate the force over incremental displacements, what we get is the work done. So this is the work done. And the work done as we increase that force from 0 to this point should be equal to the strain energy of the body. By conservation of energy, all the work that we do into deforming this body has to be stored in the body as strain energy in the absence of other dissipation, such as friction or plasticity. If you increase the forces from 0 to a value, and it results in some deformation of the body, that will be stored as the strain energy. So the area under the force displacement curve, this is the strain energy. This can be called U. There is also this region above the, let the force be P and displacement be delta. There is also this region which is lying above the force displacement curve. Let this region be called U star. And this is called the complementary strain energy. And yes, you can see if you consider a strip like this and integrate from 0 to P, so this is integrated from 0 to delta, what we have is the complementary strain energy. U star is equal to integral 0 to P. You have the displacement as a function of the applied load P, and you're integrating over incremental loads. So this is the complementary strain energy. Up to this point, it is fine. Now, what the theorem states is that suppose we have a body which is already in the deformed configuration. There is a system of forces acting on the body, and it has deformed to some shape like this. In the deformed configuration, the body has got its own. In the deformed configuration, it has got some complementary strain energy due to the effect of all the forces acting on it. We are not interested in what forces they are, but there is some complementary strain energy which is given as the sum over all forces integrated from 0 to Pi, delta I of P, dPi, something else, sum over all such forces. There is some complementary strain energy which is there. Now let us take one point on the structure and apply a force R. Suppose we take one point on the structure, let us call that point as J, and we apply a force Rj to that point. And in the deformed structure, if the point displaces by delta J, so it's already deformed, it is storing some strain energy, and the complementary strain energy is given by this. And in this configuration, we apply a very small incremental displacement delta J. So when we do this chain, the complementary strain energy increases from U star to U star plus delta U star, because you're adding a force that is deforming the structure further. So there is some change in the complementary strain energy. What is this equal to? It is equal to this system which is already there. So you have something which is already there, plus the additional complementary stimulus. So you're doing an incremental displacement delta, and associated with that there is a incremental force. That force is R. So you have an incremental delta G multiplied by an incremental force that you need. So it's delta RG. So the idea is this: we have an initial, you have the complementary strain energy which is given by this expression, and among all you have this expression for the forces, and take one of the points. So these are all points 1, 2, 3, and you take one such point J, and you apply an incremental deformation to that point. So suppose you increase the displacement at that point by delta G, the corresponding force becomes Rg plus delta Rg. So what will the complementary strain energy become? It will be delta J, which is the displacement, multiplied by Rj plus delta Rg. But if you collect all the other terms together, that is actually equal to the previous whatever complementary strain energy it initially had. So therefore, you have this relation delta U star is equal to the displacement at that point multiplied by the incremental force. So this is the complementary strain energy. Right? You take the displacement at that point and you multiply by the incremental force. This is equal to delta G into the change in Rj. Now you divide both sides by delta Rg and take the limit delta Rg tending to 0, which results in the displacement at the point J is equal to the partial derivative of the complementary strain energy with respect to the force Rg. So this in the limit delta Rg tends to 0, this ratio becomes a derivative. And since there are many such forces R1, R2, R3, this is a partial derivative with respect to Rg. This is very useful while solving problems in which forces are treated as unknowns. So let us look at this problem, which appeared in late 2011. So it's an interesting problem. It appears a bit complicated in the first sight, but it's actually very simple. So we are given a rigid beam. So although it looks like a problem in structural analysis, it is actually a problem in strength of materials. You have a rigid beam which is supported by a hinge at the left end. Let us call this point A. You have two springs, one at the midspan. Let us call this point B and this point C. The spring constants, if the text is too small, I can zoom in. So it is given that the spring stiffnesses are K and K respectively. Both have equal stiffness, K and K. And the first question, this is a linked answer question. So there's a paragraph based on which we should answer the other two questions. So the first one is to find the displacement, find an expression for the displacements delta 1 and delta 2 in terms of the load P and the spring stiffness K. And the second is to find the reactions R1 and R2 for a specified magnitude of the force P. So although it appears a bit complicated, it is actually very simple. So in general, for GATE, you need to filter out what are the information that is, what are the pieces of information given in the problem which is useful and which is useless. Here, if you see, this point is anyway hinged. So this condition that the support is actually fixed to a brick wall is a redundant, it's a useless information. It is not going to help us solve the problem. So first, what is the useless information? So that shouldn't confuse your problem solving step. It doesn't matter how this hinge is actually attached here. All that we need is this beam, rigid beam is hinged at the point A. And the next useless information is you have a rigid wall which is inclined at 45 degrees to the horizontal. So you don't need that fixed. And this also doesn't matter at all. If it is fixed, it's just you just have a hinge here. It can even just be a point. So this angle is also useless. So don't worry about those. Only look at the pieces of information which are useful for solving the problem. So as I said, the first thing is to state what all information we have. So first thing is to state. First step is to state the info. That is pretty much there. You have the span is 12. So what is useful for us to solve the problem? The force deformation relation. Suppose the forces in the springs are F1 and F2 respectively. They are given that it is a linear elastic spring. So this is a useful information. And the spring stiffness is K. So let us assume that delta 1 and delta 2 are the displacements of the springs, and F1 and F2 are the forces in the springs. What we know is F1 is equal to K times delta 1 and F2 is equal to K times delta 2. So this is given in the problem. And what we know is it is hinged at A. So the rigid beam is hinged at A. So that point cannot displace. And we also have a force of magnitude square root of 2p acting at 45 degrees with the horizontal at this point C. So this is the given information. The next step, as usual, is to isolate the body and draw the free body diagram. So let me go to the next page. So this is what the beam looks like. Sorry. This is what the beam looks like. You have an unknown force F1. You have an unknown force F2. The force, there is an inclined force of magnitude. So these are reactions. Let me draw the known forces in red. So there's an inclined force of magnitude root 2p, which is at 45 degrees. We can always resolve the force along its vertical and horizontal components. So it has a vertical component of root 2p cos 45 degrees, which is root 2p by root 2. So I have a vertical force of magnitude p and a horizontal force of magnitude p. We also have the reactions coming from the hinge. Let us call them AX and AY. And we know that it is hinged at this point, so this point cannot have any displacement. So this is the free body diagram of this. What is the third step? Third step is to enforce all the governing equations. So the first one is equilibrium equations. So let us write that. Equilibrium equations, if you set the sum of all forces along the x direction equal to 0, we get AX plus this green component, the horizontal component of P, which is P equal to 0, which means AX is equal to P. So we got the horizontal reaction directly, but that is not what the problem is asking for. Let us set sigma Fy equal to 0, in which we have AY plus F1 plus F2 is equal to P, the vertical component of the force. And let us set sigma mz about which point equal to 0. Let us take about the point A, because there are two unknowns at this point A. Let us get rid of one of them. In that case, so the span here, this is L, this is another L. So we have F1 acting at L, which produces a clockwise moment, so a counterclockwise moment, so it's a plus, and F2 acting at 2L, that also produces a counterclockwise moment, so there is a plus, and this downward force produces a clockwise moment, so there's a minus T times 2L equal to 0. So this is one equilibrium equation. This is another equilibrium equation. How many unknowns do we have? There are 1, 2, 3. 3 unknowns. But we have only 2 equations. What are they? These 2. This we have already solved for. So you can take it as 4 unknowns: AX, AY, F1, F2, and 3 equations. But we know AX, so you just treat the unknowns here: AY, F1, F2, and we have 2 equations. So it is a statically indeterminate problem. It is statically indeterminate problem. So therefore, you need to make use of the steps 2 and 3 in 3. So I said, if it is a statically determinate problem, we can stop right here. But if it's a statically indeterminate problem, we need to look at the geometric compatibility. What is the geometric compatibility here? One condition is that the hinge. So let us look at geometric compatibility. The solution that we are looking for, the deformed configuration that we are looking for, should obey A is hinged. That is, the displacement should be 0. And more importantly, ABC is a rigid body. So if ABC is a rigid body, what are all the admissible deformable configurations? You cannot have the rigid body to deform like this. It is not a deformable beam. So this is not an admissible deformable configuration. So if this is the case, delta 1, delta 2 can be arbitrarily specified. This is hinged, of course. But it's a rigid body, therefore this beam has to remain straight after deformation. So the beam remains straight after deformation. This is delta 1. This is delta 2. And suppose this has rotated, the beam cannot translate, it can only rotate. If it has rotated by theta, in the small deformation range, you can say delta 1 is approximately theta times L, and delta 2 is approximately theta times 2L. What does this mean? Delta 2 is equal to 2 times delta 1. So this is an important geometric compatibility condition. If delta 2 is equal to 2 times delta 1, now we use the condition 2. What is the second governing equation? Force displacement. And we have already stated it. F1 is equal to k times delta 1. So it is just k times delta 1. And F2 is equal to k times delta 2, which is k times 2 delta 1. So it is 2 times k delta 1. Substitute these into the governing equation. We are not interested in AY, so forget about this equation. The question is asking only for the forces and the displacements. So substitute it into the third equation, third equilibrium equation. We get what we have is F1 times L plus F2 times 2L is equal to 2PL. Right? You have P into 2L. I'm taking the minus sign to the other side. Just substitute what is F1? K delta 1. You can cancel L on all sides because L is a non-zero quantity. Plus 2 times F2. F2 which itself is 2K delta 1 is equal to 2P. So on the left hand side, we have 5K delta 1 is equal to 2P. Therefore, delta 1 is equal to 2P by 5K. And delta 2 is equal to 2 times delta 1, which is 4P by 5K. So this is the answer to this problem. Delta 1 is 2P by 5K. Delta 2 is equal to 4P by 5K. Let us look at the options. So it is option B. Delta 1 is equal to 2P by 5K. Delta 2 is equal to 4P by 5K. Now, is there any doubt before we go to the next part? Do you have any doubt? I can take question if you have any doubt. It's clear. You can respond in Q&A or in the chat. Okay, thank you. So this is one method of solving the problem. So once you get this, the next part is very easy. What is the next part? Next part is asking for if the load is 100 kilonewtons and the forces. What are the forces? So we already have the deltas. So if the load is 100 kilonewton, it is 100 by. So it is 2P by 5K, 2 into 100 by 5K, which is 2 by 5 of this is 40 kilonewton by K. K is in appropriate units. And delta 2 is 4 into 100 by 5K. So that is 80 kilonewton by K in appropriate units. And what is R1 and R2 is what they're asking. So R1 is, forces R1 and R2. So we took it as F1 and F2. They name it as R1 and R2. R1 is nothing but F1, which is K times delta 1, K in appropriate unit. So it is nothing but 40 kilonewtons. And R2 is K gets cancelled. It is 80 kilonewtons. So the correct answer is 40 and 80. Option D. Sorry. So now this is only one method to solve this problem, which is by equilibrium. There is all. Now let us look at the other method, which is by using Castigliano's theorem. You will quickly see that this is very helpful in certain conditions. So let us use Castigliano's theorem. What is the expression for the potential energy of a spring? Say if you have a spring like this, and you apply a force F and it displaces by delta, and the spring constant is K. We know that the strain energy is given by half into F into delta. And if it is a linear elastic spring, delta is equal to F by K. So it is half into F by K, which is F squared by 2K. What is the expression for complementary strain energy? If it is a linear elastic body, the stress strain curve is linear, the force displacement curve is linear. So this is a rectangle, and the force displacement curve is the diagonal of a rectangle. And we know that a diagonal splits a rectangle into two equal areas. Therefore, the complementary strain energy for a linear elastic body is equal to the strain energy. It is not true if the force displacement relation is something like this. If it is not an elastic material, if it is not a linear elastic material, then we can't say that. In case there's a dissipation, or if there's a non-linear spring, you cannot say this. But if it is a linear spring, we can always say that if it's a linear elastic spring, we can take the complementary strain energy to be equal to the strain energy, which is F square by 2k. In this problem, we have two springs. So what is the complementary strain energy for this? You don't need to look at the direction of forces, the displacement. You don't need the compatibility at all. Directly, you can write the complementary strain energy of this problem as F1 square by 2k plus F2 square by 2k. Nothing else. There is no work done at the support. There is no work done anywhere else. So whatever work is done by the force P is only stored in these two springs. Now, what is that we want? We want to find the forces R1 and R2. So, but before that, yeah, this is fine. So suppose we set, we also have the equilibrium equations. What are they? F1 plus F2 plus Ay is equal to P. And the last one, if after cancelling out the L's, what did we have? We had F1 plus 2F2 is equal to 2P. So using these two equations, how many unknowns are there? We have 1, 2, 3 unknowns. You can eliminate one of the unknowns. Let us eliminate. So just subtract the two. You get F2 is equal to F2 is equal to P plus Ay, which means F1 is equal to minus 2 Ay. Right? Is that okay? F2 is equal to P plus Ay. So F1 gets cancelled. And here you get a minus Ay. 2P minus P is a 2P minus P is a P. So this is what you get. Now substitute this expression into the complementary strategy. So U star is equal to P plus Ay whole square by 2k plus minus 2Ay the whole square by 2k. Now what do we know? If we want to find the displacement, so what we know is that, so we know the displacement at the point A is equal to 0, right? Why? It is hinged. The point A is hinged. So the displacement at the point A is equal to 0, which means del U star by del A should be equal to 0. In this case, horizontal we have already determined, so it's only the vertical. The vertical displacement at the point A is equal to 0. So differentiate the complementary strain energy with respect to the corresponding this one, the force Ay. So the force at the point, the vertical force at the point A is Ay, and the vertical displacement at the point A is 0. So if you enforce this, if you do the differentiation, what do we get? So here you get a P plus Ay. If you apply chain rule, you'll get 2 times P plus Ay divided by 2k. And if you differentiate P plus Ay with respect to Ay, you get a 1. Plus, in this case, what do you get? You get 2 times. So this minus 2 is already square. So you get 2 times minus 2 Ay. And if you differentiate minus 2 Ay with respect to Ay, you get a minus 2 divided by 2k. This should be equal to 0. So what does this result in? If you simplify, so the 2 gets cancelled, 2 gets cancelled, you get P plus 5Ay equal to 0, which means Ay is equal to minus P by 5. Right? Now that's all. So what is F1? F1 is equal to minus 2Ay. So it is nothing but 2P by 5. And F2 is equal to P plus Ay, which is 4P by 5. Now substitute P is equal to 100 kilonewtons. In one step, you have got the answers. So 2 into 100 by 5 is 40 kilonewtons. And 4 into 100 by 5, 400 by 5 is 80 kilonewtons. So we get the same answers by Castigliano theorem and by equilibrium. So this is so I hope this is clear. So if you want to apply Castigliano's theorem to a statically indeterminate problem like this, write the expression of the complementary strain energy in terms of the applied forces and the unknown reactions. Then enforce that the derivative, partial derivative of the strain energy with respect to the unknown reactions have to be equal to 0. Why? It is because, so let me write down the steps so that it's useful for problem solving. So if for a statically indeterminate problem, using Castigliano's theorem. So write the expression for complementary strain energy. In terms of forces. If you write it in terms of displacements, you can't take the partial derivative with respect to force. You need to, it will work. You can do it. You can write it in terms of the displacements half k delta 1 square plus half k delta 2 square. But then after differentiating with respect to delta, you need to apply the chain rule. So you can also do that. But the simpler way is to always write in terms of the forces. The next thing, express the forces in terms of the reactions and the applied force. So here you will get U star as a function of all the forces, out of which some are the applied forces P1, P2, and so on. And some are the, say, the internal forces. It can be F1, F2. In this problem, they are internal forces and so on. And also the reactions R1, R2, and so on. The next step is to express the forces in terms of the reactions and the applied force. How? Use the equilibrium equations. So the degree of static indeterminacy is Ns. There will be Ns support reactions in excess. So I express the others in terms of that. So you get, say that is, you have F1 is equal to F1 of R1, R2, P1, and so on. Just eliminate F1, F2, and eliminate whatever you can in terms of the reactions. That is what it means. And F2 is F2 in terms of the reactions and the applied force and so on. So therefore, once you have substituted, U is just a function of the reactions and the applied forces. R1, R2, and so on. The next step is to enforce the geometric compatibility by del U star with respect to del R1 equal to 0, del U star with respect to del R2 equal to 0, and so on. You enforce these conditions and solve for the unknowns R1, R2, and then you get the solution to the entire problem. So this is how you use Castigliano's theorem for solving these problems. Is that okay? I hope it's clear. Let me go to the next part. So the last part of today's session is the stability of equilibrium. Until now, we have always looked at problems in which we want to. We have looked at problems where we solve for the equilibrium configuration. Okay. So until now, we have looked at problems where we don't know what is the equilibrium configuration and we are solving for the equilibrium configuration. But suppose we ask this question, given an equilibrium configuration, say, suppose I have a beam or something subjected to some load, and suppose I'm given that this is the deformed shape. Delta is no, V as a function of X is no. Suppose given an equilibrium configuration, is it stable? What do we mean by is it stable? suppose we perturb, suppose we disturb the equilibrium configuration. So suppose we apply a small displacement or a small force and take the structure from the equilibrium configuration to some other slightly perturbed configuration. Suppose we disturb the equilibrium, we know that the forces will no longer be balanced. We know that there will be a certain acceleration. Will the acceleration tend to bring the system back to equilibrium, or it will tend to take it away from equilibrium? So if we disturb the equilibrium, there will be an imbalance in the forces. So there will be resulting acceleration. Will that acceleration make the system to come back to equilibrium, or it will take it farther away? So will the system tend to return to the equilibrium, or go far away? So the classic example is you have this ball inside a bowl. Suppose we have a bowl like this, a bowl, a flat surface like this, and we have a bowl like this. In all three cases, whatever I have drawn is an equilibrium configuration, because if you take the vertical, you have, if you take the forces, there's a downward force due to the weight, and you have the upward force due to normal, and they act along the same line. If it's a circular, perfectly circular ball and circular surface, in all cases they can be perfectly balanced. There are no horizontal forces, there is no movement. So all three are valid equilibrium configurations. So all are valid equilibrium configurations, but which of them is stable? Suppose I apply a small force to the right side here, the forces will no longer. So this is an imbalance force. Let us call this force F. If I apply this force to this very small perturbation, if I displace the ball slightly, it will no longer be in equilibrium. So the downward force, so what will happen if you displace it slightly? The downward force will be like this, the downward force will be slightly away. This is an exaggerated view. It will not be in equilibrium. There is a resultant unbalanced force in this direction. Therefore, there will be a net acceleration towards this. But what will that acceleration do? That acceleration is trying to bring the ball back to its equilibrium configuration. So this is a case when there is stable. If the imbalance in the forces results in an acceleration that brings the system back to its equilibrium configuration, then it is stable. What happens here? If I slightly displace the ball by delta, the normal force will be like this, the vertical force will be like this, they will be imbalanced, and there is a force like this. But what will that force do? That will make the ball accelerate in the same direction as the direction of the perturbation. Here I am disturbing it in delta, but the acceleration is in the opposite direction. Here, if I displace it by delta, the acceleration will push it farther from equilibrium. So the ball will just run away. So this is an unstable configuration. So this is an unstable equilibrium. This is a stable equilibrium. What will happen here? Here, if I push it by a small delta, nothing will happen. It will continue to be in equilibrium. So this is called neutral equilibrium. So the idea of stability is only so much. You have an equilibrium configuration. You disturb the equilibrium by a small amount. What happens to the uh, system? That is what we look at. So one standard example, simple but a very nice example is this. So this was directly asked in GATE 2008. We have a rigid bar. Sorry for the size, it is small. We have a rigid bar GH of length L supported by a hinge at G. There is a spring of stiffness K as shown in this figure. What will be the buckling load? What is buckling load? So we define the buckling load. We'll see what the buckling load is. So it is the margin between the values of load for which the straight configuration is stable and unstable respectively. So if you have P less than the critical load P critical, then the straight configuration is stable. And if P is greater than P critical, the straight configuration is unstable. Okay. What do I mean by straight configuration? Let us see. So let us take this system. This is a rigid bar, free to rotate on both sides. What are all the forces acting here? Here you have, initially the spring is unstraight. So you have, say, K. There's a force P applied here. There will be some support reactions coming here. So initially, in this configuration, just P is equal to Gy, Gx is equal to 0. Let us call the force in the spring as F equal to 0. So this is a valid solution. You can see all conditions of equilibrium are satisfied. These two, so this acts as a two-force member. The two forces are collinear. So moment equilibrium is also satisfied. So this is an equilibrium configuration. Now the question is this configuration stable? To answer that question, let us displace the bar slightly. So this is an exaggerated view. Let us take it, let us slightly displace the bar by a distance x without disturbing the forces. So in that case, the force P still acts here. There is a Gx and Gy. But now what is the issue? Moment equilibrium will not be satisfied. So if we slightly displace the bar by x and take moments about g. Let us take sum of all moments about g. We can't set it equal to 0, right? Why it is not equal to 0? Because it is not an equilibrium configuration in general. You just take the moments about g. We have a counterclockwise moment due to p. So p acts at a distance x, which is plus px minus. So k, if it is moving this side by x, you will have a force towards the left. The spring force will be towards the, sorry, if it is displaced in the left direction, the spring force will be towards the right. So F is equal to minus kx. So there's some clockwise moment due to the spring force, which is kx acting at L. Now there are two actions. So this is the net moment. Now this has caused the bar to rotate counterclockwise by theta. Now if the net moment is, if the net, so this is an unbalanced moment. If the net unbalanced moment is trying to bring the system back to the straight configuration, then it is stable. Therefore, if the net unbalanced moment is negative, then equilibrium is stable. The straight configuration is stable. On the other hand, if the net unbalanced moment is also in the counterclockwise direction, so theta is positive taken counterclockwise, and if the net unbalanced moment is also trying to push the bar further to that side, then the straight configuration is unstable. Now let us examine this. Remember, x is a very small displacement. So the condition for stability is px minus kxl should be less than 0. So condition for stability is this. So let us rearrange. We get px less than kxl. And this should hold for very small displacement x. X is not equal to 0, right? We have displaced it slightly, which means p is less than kl. So the condition for stability is p is less than kl. And the condition for unstable is p is greater than kl. So what is the critical low? So the critical, so p, if p is less than p critical, it is stable, and p is greater than p critical, it is unstable. Therefore, p critical is equal to kl. That's all. So very simple problem. In this case, we have so the load at which the system transforms from stable to unstable is KL. So the correct answer is option C. P is equal to P critical is equal to KL. Is that okay? Okay, I hope it's clear. So this is the idea of stability. Note that it doesn't mean if you increase P, if you increase P from 0 to whatever, if you increase P from 0 to P critical, it doesn't mean at the value of P critical you will have infinite displacement. It means that there are two possible equilibrium configurations. So as you increase P from 0 to P critical, so if this is the value of P critical, and this is say X, and this is P. At P critical, you can either have a deformed configuration where X is unbounded. So X can be anything at P critical, or X can also be 0 and it can continue further. So this is called a bifurcation. This is called a bifurcation point. So this is the path. As you increase the load from 0 to P critical, for P less than P critical, there is no other equilibrium configuration. You only have this one. But for P greater than P critical, you can either have this or this. But this is unstable. So if you slightly disturb, even if you maintain the bar at this stage, if you slightly disturb, it will come back to this. So that is why stability is an important aspect while designing structures. Say if you have a column in a multi-story building and the load P is greater than P critical, while we construct the column, it can be it can remain stable. But because of some slight wind load or something, we don't want the column to buckle and go to some other configuration like this. It can still be in equilibrium, but this transition from equilibrium to the unstable to the next equilibrium involves acceleration. In that case, it undergoes very large deformation in a very small time, which can damage and it can cause danger to the life and property. Now, so that is the idea. So the other related topic in the stability is stability of columns. So let us take the same example we just looked at. Let us take a simply supported column. Let us take a simply supported column. This condition, let us make it a column with a roller, otherwise it cannot deform. Subjected to some force P. The force P. Now what happens as we increase the load P? The column can either remain straight or it can also take up a curved configuration. It can curve like this, but it can also remain straight. We don't know which is favored. Now let us examine the stability of the straight configuration, straight column. If the column continues to remain straight, let us see if that configuration is stable or not. How do we do that? Disturb the equilibrium by. So what in a straight configuration, the solution is simple. The reaction at this point, the vertical reaction is just P. All the horizontal reactions are 0, and therefore it satisfies equilibrium. That's all. That is the end of the problem. But if it is not, then we need to examine the stability of the straight column. So let us displace it by some V of X. Let us displace the column by V of X. So in that place here, in this problem, we just displaced it by X, and everywhere else it is determined because it's a rigid bar. Here it is a deformable column. So let us consider a displacement, a very small disturbance V of X. In that case, what will be if we write the equilibrium? So you have something like this. There will be a bending moment in this direction. Let's call it M of X. It's a force P. Because of equilibrium, vertical equilibrium, there will be an equal and opposite force P. And at this point, the displacement is V of X. If you write down the equilibrium, we have there's a couple. There's a counterclockwise couple, which is P times V of X is equal to what? M of X. Right? M of X is the counterclockwise moment. Sorry, the clockwise moment. And P of X is the counterclockwise couple. P separated by V of X, which creates a counterclockwise couple. And M of X is like this. As I said, okay, you can't put an M equal to. What we can say is there is a counterclockwise couple which tries to destabilize the column. So straight configuration is like this. If you have a counterclockwise moment, it tries to bend. So this is kind of destabilizing. The counterclockwise is destabilizing and the clockwise moment is stabilizing. So the difference is the net moment M. Let us take this as the net moment, net unbalanced moment M. Now, if the net unbalanced moment m is acting in the same direction as the destabilizing, so it has already rotated in the counterclockwise direction. If m greater than 0, we know it is unstable. And if m is less than 0, we know the configuration is stable. So if what is the condition for stability? We want p v of x minus m of x to be less than 0. And we know from the beam bending theory, what is m? That is the moment curvature relation. Very simple. It is ei d square v by dx square. Right? Is this okay? If not, let me write down. So you have a beam like this. It has rotated like this. V of x is increasing in this direction. This is m. So m is equal to, you can take the stresses in the cross section. You'll get m by I is equal to epsilon by r, and where 1 by r is, so you get sigma by E. So basically you have the sigma is equal to my by I, which means the strain is equal to my by EI. But the strain has a linear distribution, so we can find the strain itself is equal to 1 by r into the displacement. And if you do all that, you get this. This is y by r. So y and 1 by r is d square v by dx is equal to uh, my by ei. Therefore, the moment is equal to ei d square v by dx. Right. So let me check. P v of x. So when you take the sign convention, m of x is positive in this direction. Okay, the direction I have assumed is incorrect. So if you take the beam, so this v of x is measured upwards as possible. This is upwards as positive, right? So you need to take the beam deformed configuration like this. So you have P and a P, and you have bending moment like this. And in this case, it's the same thing. So that's fine. So you have PV minus EI d square b by dx square is greater than 0. So this value should be less than 0 for stability. So 1 minute, let me check. So if you have a oh sorry, sigma, there's a minus sign here, right? So sigma is equal to m minus my by I. So under a sagging moment, at the top you have a compressive force. So compressive stresses are taken as negative. So there's a minus here, but epsilon is equal to y by r is fine. So you have a minus y by r here as well. And the radius of curvature, so if it is increasing in this direction, the curvature is taken as negative. So you get another minus here. Therefore, the relation is d square v by dx square is equal to minus m by n. That is, if the dv by dx is increasing, you get a sagging moment. Let's check. So yeah, that is fine. So the governing equation becomes PV plus EI d square V by dx square equal less than 0. Let us consider the case where it is in neutral equilibrium. So this is stable. For the condition of neutral equilibrium, we have EI d square V by dx square plus P equal plus PV of x equal to 0. We can solve for this directly. So assume V of x is of the form e power lambda x, and then substitute in the governing equation, we get EI lambda square plus P into e power lambda x equal to 0. E power lambda x cannot be equal to 0. Therefore, lambda is equal to plus or minus I root P by EI. So e power I root P by EI, let us call it plus or minus I omega. So e power I omega can be written as cos omega. So e power I omega x can be written as cos omega x plus I sin omega x. So you can also, so the general solution is V of x is equal to a e power I omega x plus b e power minus I omega x. But this itself is a cos omega x plus I b sin, I sin omega x plus b cos omega x minus I sin omega x. So just rearrange, you can call a plus b as c and a minus ia minus ib as d. So you get it is as some c cos omega, where omega is root p by ei x plus d sine root p by ei x. So this is v of x for which the equilibrium is stable, neutral. And what are the boundary conditions? We know v of 0 is equal to 0 and v of L is equal to 0. So v of 0 equal to 0 means, so this term will vanish, we get c equal to 0. And this means d sine root p by ei x is equal to 0. So if you set d equal to 0, we get straight configuration. But that is not what we want. We are displacing it by a disturbance v of x to see if that is stable or not. So this is a trivial solution. We don't want to look at this. Let us look at the other case when d is not equal to 0, which means sine of root p by ei x should be equal to 0, which means L. This is evaluated at L, which means root p by ei L is equal to, it should be n pi, an integral multiple of pi. So square on both sides, we get p by ei into L square is equal to n square pi square for n equal to 1, 2, and so on. Therefore, p is equal to n square pi square ei by L square. So this is the critical value. If p is greater than this, what will happen? If p is greater than this, if it is equal, we saw it is an equilibrium. Therefore, even after perturbing, the system continues to be in the state of equilibrium. If p is greater than that, what will happen? The net moment will be in the direction of destabilizing. So the net moment will try to destabilize the column, and if p is less than that value, it will try to stabilize the column. So that is the critical value. P critical is equal to n square pi square by ei by L square, where n is equal to 1, 2, and so on. Now, so you see that there are multiple values for corresponding to different shapes. So if the shape is like this, the critical value at which it happens is pi square ei by L square. For this, it is pi square ei by L square. The shape is 2 times. So if the shape is sine 2 pi x by L, that is something like this. Then the critical load is 4 pi, n square is 2 square, or 4 pi square ei by L square. And if the critical load is 3, you have something like this, 9 pi square ei by L square. But we don't know in real life which kind of disturbance will occur to the column. So it is better to take the least. So P critical for this column is pi square ei by L square. Now, based on this, we have one question in GATE 2008. So the cross section of column is consisting of two strips, each of thickness T and width V, as shown in the figure below. They're asking the critical loads in two cases. In one case, the two strips are attached, so they are glued together by a perfect bond. So what do we mean by perfect bond? I've already explained in the case of when I did concrete. So perfect bond means strains are continuous. So if you take a point at the center on this strip, the surface of the strip and this strip are perfectly bonded, which means the displacement of both the points are the same. So there is no slip between the two. In that case, if the two segments are perfectly bonded, then the strain distribution in the cross section when it undergoes bending will be something like this. So it is perfectly bonded, the strain distribution will be something like this. It will be continuous. The displacements will be continuous, so the strains will be continuous. But if the strips are not perfectly bonded, let me put a small gap there. There's no gap, but they're just sliding over each other. So what happens is when it buckles, if it is perfectly bonded, if you see this view, you see this view. When it buckles, it acts as when it buckles or bends, it acts integrally. So there is shear transfer. The shear forces. So it buckles like this if it is perfectly bonded. And if slip is allowed, then there is no shear stress at this surface. So what happens is it will buckle something like this. Buckle or bend doesn't matter. In either case, it will bend or buckle like this. There's a slip in between. So it looks like two parallel columns buckling together. Right? That is the difference. So in one case, the moment of inertia, let us call in one case the P case. In the first case, perfectly bonded. The moment of inertia is given by the usual thing, h cube by 12. So B into what is h? It is 2t whole cube by 12, which is 4b. Sorry. So here we have here we have 8b t cube by 12. So 4 gets cancelled. You get 2b t cube by 3. In the other case, where they are not perfectly bonded, the moment of inertia is of two individual beams. So if it is not perfectly bonded, this will have a linear distribution. This will have another linear distribution. But in between, the stresses are not continuous. The stresses at the interface are 0. There is no continuity of stresses. So here, this will be under, if it is perfectly bonded, this will be under compression. This will be under tension. If it is not perfectly bonded, this will be under compression. This will be under tension. This will be under compression. This will be under tension. So it is like two beams bending individually, but they are just together. So you can just add the moments of inertia. So it is V t cube by 12 plus B t cube by 12. So this is B t cube by 6. Now the critical loads of the column with perfect bond and without a bond are P and P naught respectively. So next it is easy. So P is equal to pi square E I where it is perfectly bounded by L square. So here it is pi square E by L square into 2b t cube by 3. And what is P naught? P naught is pi square E I corresponding to the slip case by L square. It is pi square E by L square into b t cube by 6. So divide P by P naught. This will get cancelled. You get 2 by 3 divided by 1 by 6, which is nothing but 4. So the correct answer to this question is 4. So note that if you have proper shear transfer, the column is 4 times as strong as if you allow slip between the two pieces. So that is what it is. So that brings us to the end of today's session. If you have any doubts, you can ask. If everything is okay, you can tell me. If I'll wait if you have any doubts. Is there any doubt? Is everything okay? Yeah, you can feel free to interact. You can tell me if you have any issue in that in some part, or even if you have some questions from the other sessions, you can ask. And as I said, you can also post it in the video. So let me wait for another 2 minutes. If you can go through this. If you have any doubts, you can ask. I'll wait. And after 2 minutes, I'll log out. Okay. So thank you for attending. It seems there is no doubt. So thank you all for attending. As usual, I will be uploading the recording to YouTube, and the course content can be the presentation I'll be uploading to this. So you can go to this groups.google.com and you just search for this. Just search in all groups and messages. NPTEL Gate C 2023 and so on. So it shows this. Just click and then you can join to the group. So I'll be uploading the session to this. Thank you for attending. See you next week.